All right, so now that we have done some specific cases, so we've tested the case of like 0, block 60 or byte 63, byte 64, 65, right around the byte boundary, counter wraps, but there are an enormous number of possible combinations that could go into this. So unit testing can be useful for these individual cases, but we need to apply some techniques and formal methods in order to actually be confident in this. Confident that this is error-free and this is correct. So we need to develop a proof that this is correct. So we can have, start at block 0 and we can go all the way to block 2 to the 32nd minus 1. And that's a huge space, and we're not testing everything in there. We're only testing a couple of cherry-picked examples. So let's go into our source. And let's go to where we're checking for if the next counter range is available. So we are going to write what is called an ACSL contract, which is basically a formal behavioral contract for a C function. We're going to have preconditions, postconditions, and assigns. So this is how, where's my app? This is how the contracts are specified, is they have their own kind of comment looking block like this. So for this one, we are assigning nothing. This little helper is going to be a pure decision function. It's going to take 2 integer values. There's no caller visible memory changes, and it returns whether the range is available. So we're going to say assigns nothing. We want to ensure a Boolean result, because the next counter range is either going to be available or it's not going to be available. So that is either a true or false. So the result is going to be 0, or the result is going to be 1. So this is very important because the function returns an integer, but an integer can be a wide range of numbers. This contract promises that only the 2 Boolean representations are going to be coming back. So only 0 and only 1. That means if somewhere in here that we put, it could return a 2 or it could return a 75, those are going to be rejected. Then we are going to say that this ensures an exact result where the result does not equal 0, and then we're going to do this double arrow if, and this means if and only if. So basically we're proving both directions. Every allowed request satisfies the mathematical rule, and every request satisfying the rule is allowed. If we were to do this as a one direction implication, that would be a lot weaker, because that would prove that the accepted inputs are safe while still permitting legal inputs to be incorrectly rejected. So we don't want to be doing one direction implications on this. Now our block space is 2 to the 32nd. So this is the total addressable integer space. So we want to look at when our length divided by the XCP cha 20 block size is less than our total addressable space minus the counter, or length divided by the XCP cha 20 block size equals, let's break this up into two lines. Or minus the counter and the length mod XCP cha 20 block size is equal to 0. Open. Close. So 1, 2, 1, 2. Okay, that was good. So I guess in plain English, the way to look at this is the number of counter values still available when we're including the current counter value is the available is 2 to the 32nd power minus the counter. The number of cha 20 blocks needed for a given length of bytes is, so the number of blocks needed for a length. So we can essentially say that our result so we want to return true So functionally, this is what we're trying to express here. So we want to return true exactly when the number of blocks required is no greater than the number of counter values remaining. So we have 2 to the 32nd is this number. So if we have, like, let's say the counter is at 0, then we have this many blocks available. When the counter's at 1, or we can when the counter equals 1, we have 2 to the 32nd minus 1 blocks available. When counter is at our uint 32 max, then we have 1 block available. And remember, this uint 32 max, this is just the highest number of the highest number that a 32 bit unsigned integer can store. So that's the ceiling that we're running into there. So the first allowed case would be that the length divided by 64, because that's the block size, is less than the blocks available. So if the number of complete blocks is smaller than the available target, there is still room for a possible partial final block. So if we had like the number of whole blocks we had left was 3, and then we had available was 4, then the remainder can be anything. Oh. So that's our first allowed case. Our second allowed case is when the whole blocks are equal to the blocks available, and well, we can just put we're not writing code, but and the remainder is 0, then the whole blocks exactly consume like our budget. The request is legal only when there's no remainder. A remainder would mean that we need 1 additional counter value. So if it was like whole blocks, we have 4, and then we had 4 available, and the remainder was 0, that's fine. But if the remainder was 1, then we have to reject it. So let's go ahead and run our cursory first check on this now that we have this. So we're going to use the Frame C tool. The architecture that we're on is x86-64. So it's going to be x86-64. We will need a couple of extra arguments here. And I will include these in the GitHub repository because they're kind of just specific to the tool usage here. Obviously, since we're doing C99, generally we don't need C++ extra arguments. Include. Ooh, I made a typo. Let's see. Ooh, I misspelled assigns. And I probably forgot a semicolon. I sure did. This line has a semicolon. This line needs the colon. This line has a semicolon. This line needs a colon. Okay, I think that's good. All right, so we can see we proved 10 goals. This one didn't, or 9, sorry, excuse me, 9 of 10. There was a timeout. A timeout doesn't necessarily mean it's wrong. In a lot of cases, these can take a fair bit of time to discharge. We can rerun this, however, with some different, what is it? I think it's WP prop, and then we can change the prover, and we need to print WP prover none, WP print. Okay, so WP introduced shorter symbols here. So X here is going to be the whole blocks, and X1 is going to be the counter plus whole blocks, because you can see the counter plus whole block. So it's setting variables here. All right, actually, let's whiteboard this out a little bit. So X is whole blocks x1 is the counter plus whole blocks. Let's just say counter plus x. And then, so if 2 to the 32 is less than or equal to the uint64 representation of whole blocks. So if the request contains at least 2 to the 32nd whole blocks, our implementation immediately returns 0. Here. So if x is greater than or equal to 2 to the 32nd, we will reject. So let's see. But our contract contains a legal clause where there is no remainder and the counter plus the whole block count equals exactly 2 to the 32nd power. So the double arrows say that in this case, the function must return non-zero. So the second. So x1 is counter 0 plus x. So if x is 2 to the 32nd, then x1 is also exactly 2 to the 32nd. So zero plus 2 to the 32nd, 2 to the 32nd, because I mean, adding 0 to a number is just a number. So in our implementation, we are saying that x greater than or equal to 2 to the 32nd, the result is 0. But in our contract, we're saying x1 equals 2 to the 32nd, remainder 0. The result does not equal 0. The same input makes the implementation return 0, while the contract that we wrote here requires non-zero. So that's the disagreement causing the issue. So the length len equals x times 64 equals 2 to the 32nd times 2 to the 6th, which is 2 to the 38th bytes. All right, so now that we know that this is not going to discharge correctly, let's fix our implementation. Now, we don't want to change our contract. Our contract is the requirement, so we do not want to touch that. So let's just can our logic. The remainder and whole block calculations don't need to change. Okay, so for our blocks available, we need to first calculate the actual number of counter values available from the starting counter. And then at counter 0, this will correctly produce 2 to the 32nd blocks. So then we need to reject when the complete blocks alone exceed the available counter budget. So if a cast U in 64 T of whole blocks is greater than the blocks available, we will just return 0. Now also notice that this uses greater than, not greater than or equal, so exactly consuming the available budget can still be legal. Now for the return, we will return the remainder So after that first check, the whole blocks are either below the budget or they're exactly equal to it. So if there is no remainder, either case is legal. If there is a remainder, the whole blocks must be below the budget so that one counter remains for the leftover block. So if you had even if you only have 1 byte left over, you need a new block because you have to increment the counter and the counter addresses 64 bytes. So we would do in 64T. So basically, if we have three whole blocks, 4 available blocks, remainder is 1, we're good. If we have 3 whole blocks, 4 whole blocks, 4 available blocks, and the remainder is anything other than 0, then we need to reject it. So now that we have that, we can rerun and retest our frame C. go, and I need to fix that error. Okay, apparently I've been fat for green things. My guess is I made another mistake. Yes, I used the wrong arrows here. Oh, and I did not define a type U in 64. Okay, so we now have proved for our counter range that there is no invalid case. We don't have to go through and test every available case because we've algebraically ruled it out. I would say if you're doing formal methods yourself, whenever the prover times out, the first thing, at least I make a lot of mistakes, so the first thing that I would look for is small mistakes like that. So we started with a helper that passed our example tests, our cherry-picked ones, but it rejected one legal extreme request, so that's a counter 0 with exactly 2 of the 30-second blocks. So now our ACSL contract stated the rule independently of our implementation. We couldn't prove it. We went back, changed the implementation, and proved it. So after correcting the comparison and my typing mistake, we've proved all 9 obligations, including the exact result contract. We can also do one simple thing here. If you see this says missing RTE, RTE is the runtime error analysis that FrameC supports. They're like plugins that add assertions that have to be proved to show that like the C code can't trigger undefined or some kind of erroneous behavior at runtime. We can actually just add that in. If we just add There we go. So I will call that here.